Hello everyone, this is Dr. Hopkins narrating the next video in our series for 472, and we're going to continue discussing mixing of volatile liquids. So in the last video we established the concept of ideal solution behavior, or Raoult's law. So that's the behavior of something that may be like a solvent in a very dilute solution, and then we compared that, or we compared the behavior of our liquid to if it was an ideal solution behavior. And that's where we established this concept of activity. And we have to have a comparison. Okay, so we're going to introduce a new standard state or reference state called Henry's law. And basically Henry's law is what you would use to approximate the behavior of say a volatile solute or even a gas that's dissolved in a dilute solution. So let's set this up. A is our solvent, B is our solute. We're going to call it a dilute solution. So the mole fraction of A approaches 1. The mole fraction of B approaches 0, establishing that being dilute. So let's take our chemical potential of our solvent, just like what we had before. Notice we're just related to the mole fraction, because in this case, if this is like the solvent, we're going to assume that the activity coefficient of our solvent is pretty much 1. So our activity and mole fraction are the same. And then we need to establish the chemical potential of our solute. So we're going to compare that. So in other words, this is compared basically to Raoult's law. Here we're going to compare to Henry's law. And so our chemical potential of our solute B, reference state. So now we're going to have this RT natural log. Once again, we have our mole fraction, but now we're going to compare a Henry's law constant to the vapor pressure of B if the liquid were all B. Okay, so that's our chemical potential, and Henry's law itself, so the vapor pressure of B is just the mole fraction times this Henry's law constant. Okay, so where does this apply? Let's look at a plot. So here we have vapor pressure of bromine, so we're going x 0 to 1. So in the low region, this is and actually it's in carbon tetrachloride. So at the low region, our bromine is a solute in a very dilute solution. You can see we have the Henry's law extrapolation to this Henry's law constant. Now there are tables of these we can look up. It's typically a pressure, but is not the same as the pure liquid vapor pressure, because the pure liquid vapor pressure is the comparison for Raoult's law. And so you'll notice it tracks along pretty well along the Henry's law plot until we get high enough concentration. Now we're not a dilute solution, and you'll notice the behavior no longer tracks either one of the Raoult's law or Henry's law plots until we get to relatively high 0.8 mole fractions, and at that point it tracks along with Raoult's law once again. Okay, so comparison to Henry's law gets the solute, comparison to Raoult's law gets the solvent behavior pretty much or close to correct in many mixtures at those extremes. Okay, so let's look at a plot of a mixture comparing, and in this case we're just going to compare to Raoult's law. We could apply a Henry's law constant, and actually the Henry's law we would fit, and the Henry's law constant for chloroform would be somewhere here. We'd fit this low end here, and the Henry's law constant would fit to somewhere around there. All right, so if we were to explain these first few points where each of these component acetone and chloroform are the solute, we would use Henry's law, but I'm neglecting that at this point. We're just looking at this. In this case, you'll notice the Raoult's law plots of the two, and we have our vapor pressures of the pure. And in each case, the vapor pressure is actually lower than what Raoult's law predicts. So we have an escape tendency of our liquid in this mixture that's less than 1. So what that means is that this solvent and solute are miscible, right? They're favorable intermolecular interactions, and so they're going to stay in solution rather than escape into the gas where there are no intermolecular interactions. So that's an example of a mixture of chloroform and acetone. It makes sense. It mixes pretty well. So let's show an example where we have positive deviations from being an ideal solution. And so we're comparing Raoult's law, and here is carbon disulfide and acetone, two components that are completely different. And you'll notice now, of course, if we were to do a Henry's law plot for carbon disulfide, it would extrapolate way up here off of the graph. And for the acetone, it would also extrapolate way up off the graph. So the Henry's law constants depend on both the solute and the solvent. Okay? Because remember, acetone would have, in the previous plot, acetone extrapolated, the Henry's law constant extrapolated to somewhere around 200 torr, whereas here it would extrapolate to well over 1,000 torr. Okay, anyway, so comparing to ideal solution, we have once again our Raoult's law on dotted lines, and you'll notice in each case the deviation is largely, so the vapor pressure is much higher than what Raoult's law would predict. So we have a greater escape tendency than ideal. So the activity coefficient is greater than 1. These are immiscible solvent and solute. The intermolecular interactions are so unfavorable that they push into the vapor where they will have no intermolecular interactions. And that's what you get when you have positive deviation from an ideal solution. So this is how we use both the Raoult's law and Henry's law to kind of explain, okay, are these two combinations miscible, and then why, with respect to intermolecular interactions, and then are these two combinations immiscible, and why? Or is this a good solute in a dilute solution with a solvent, and so forth. All right, until next time.